So now we're going to take a look at the exponential distribution. So the exponential distribution is interesting because it links in with another distribution that we've already had a look at. So the exponential distribution represents the time between Poisson events. So we talked about Poisson earlier on, and we talked about its relationship or similarity, at least to binomial, being that it's a discrete distribution. We have a constant average rate. They need to be independent of each other, happen singularly. But this time we have no upper limit. And we're just counting how many times things happen. So because the exponential distribution is the time between these events, that means that the exponential distribution is a continuous distribution. So because we're talking about time here, that means that we are saying that this is continuous. So that makes it similar, in a way, to the normal distribution in the fact that less than and less than or equal to notation are going to give us the same value because we can't count an exact value. That also means if we're looking at the probability of x equaling anything, it's going to be equal to 0 because it is continuous. So another important thing is that we say that the exponential distribution has what we say no memory, which means that it does not take into account the time since the last event has happened. It only looks how long from now until the next one occurs. So if in a question it says, John has waited half an hour, what's the probability that it has to wait less than half an hour until the bus comes? Then we don't take into account the fact that he's already been waiting there half an hour. We're only finding the probability that it's less than half an hour until the next one comes. So that's quite important to remember, and it's quite a common trick that the exams try and catch you out on. So the exponential distribution is a little bit different because we have to try and find the probabilities of the exponential distribution using this cumulative distribution function here. And as you can see, this is meaning that we're having to put some stuff into our calculator to get the values. Just another thing to point out is that here, this is a capital F. That means that it's a cumulative distribution. Don't get this mixed up with a little f, which gives us the probability distribution. So this one's cumulative, this one just gives us the probability at that time. So just be careful with that. So as the exponential distribution is a continuous distribution, we cannot find equal or exact values. So I just pointed that out a little bit earlier. That's just going to give us 0. So just adding a little note here. That means that the probability of x equaling anything is going to be 0. And the probability density function is this one here. So you could be given the information in a range of ways. Okay, you could be given the information like this, or you could be given the information like this. And you'll notice here that we have lambda, and we should have seen lambda before in the Poisson distribution, which is a big hint that these two are linked together. So we're going to have a look through some examples. So here you can see that we have been given the probability density function. So from this, I can pick out straight away that lambda is equal to 4. That is picking it out from this, bearing in mind that it has been written in this form. Now, unfortunately, you are not given this in the exam. You have to remember this. However, we are given this information here. So that's quite important that we're given this one here, but we have to remember this one to be able to pick out what the value of lambda is. So then we can use our formula that we have here. So probability of x being less than 3. So that's going to be equal to 1 minus e to the minus lambda, which is 4, times x, which is 3. And then we're going to put that into our calculator, into the normal run math mode. So 1 minus E, which we get by using shift and then the ln button. For some reason my pupils like to call it in. Minus 4 times 3, which gives us 0.999938558. I'm not going to round that at all. I'm definitely not going to round that to 3 significant figures. The reason why I'm not going to round that to 3 significant figures is that it would just be 1, so we need to be careful with that. So then we're looking at the probability that x is greater than 6. So in a similar way as we would have done if you had the old-fashioned calculator, we have to do this now regardless of what type of calculator you have. We need to swap this to 1 minus something. Now, because this is a continuous distribution, we're changing this to 1 minus the probability that x is less than or equal to 6. Because if we want strictly greater than 6, that means that we want less than or equal to 6. So that means that we're doing 1 minus, and then we're using our formula, so that's going to be 1 minus e to the minus 4 times 6. So that's 1 minus, bracket, 1 minus e to the minus 4 times 6. And that gives us 0.378 to 3 significant figures there. You could have left that one in standard form because it was such a small number. But it's important to make sure that you understand that even if this said, let's say it said probability of x being greater than or equal to 6, which means that we would have done 1 minus the probability of x being less than 6, we would have still got the same value. Okay, and that's because it's a continuous distribution. This probability is going to be the same as this probability here. So next we're looking at the probability that we get between 2 and 4. So that's going to be the probability of x being less than 4, which would give us from 4, just less than 4, all the way down to 0, minus the probability of x being less than 2. Because if we have our number line, I've done a number line this time instead of just numbers because it is continuous, so we have to take into account the numbers between. So when we're doing less than 4, we are finding this probability here. But I only want between 2 and 4, which means I have to take off this probability here. So actually that should say less than or equal to 2 that we are taking off. But as this is continuous, this isn't going to make a difference to our distribution, to our answer here. So then we're going to do 1 minus e to the minus lambda, which is 4, times 4. Minus 1 minus e to the minus lambda, which is 4, times 2. So that gives us 1 minus shift and then ln to the minus 4 times 4 minus 1 minus e to the minus 4 times 2. Notice my brackets, these are very important, especially on the second part here. This has to be in a bracket, otherwise it's going to give you the wrong answer. And that gives us 0.0000335 to 3 significant figures. And the last one here, the probability of x equaling 5.5, we've already talked about this, that's going to end up giving us 0. Just another important thing, if we were to write down the distribution of this, it would be x follows the exponential distribution, which we write as exp, and then we put our lambda, so that would be 4 for this one. So moving on to the second example. So this time, in a particular county, the distance between successive potholes on country roads may be modelled by an exponential distribution with a mean of 125 metres. Determine the probability that the distance between successive potholes is less than 10 metres, between 100 metres and 200 metres. Now we need to be careful here because we've been given the mean, okay, the mean distance. So that isn't going to be our parameter, okay? So sometimes it will give you the parameter, sometimes it will give you the mean. In this case here, we have been given the mean and we have to find the parameter. So to get from the mean to the parameter, we have to do 1 divided by the mean. So if we've been given the mean, our parameter is going to be 1 divided by the mean. So actually here we're using x squiggle exp 1 over 125. So just be careful of that language. If it says mean, then we have to do 1 over that to get the parameter. If in the question it says that this is our parameter, we can just use that straight away. So you need to be careful with that. That's the difference between if you are given the mean and if you are given the parameter. So we are going to have a look at that a little bit more in the next section, but I just wanted to make that clear here about if it says the word mean, in order to get the parameter, we have to do 1 over that. Sometimes it will say parameter, sometimes it will say mean. They are two different things in this situation, not like in Poisson where our parameter was our mean and our variance. This time our parameter is going to be 1 over the mean, and that's very important to bear in mind. So then when we're looking at the probability of x being less than 10, we would have 1 minus e to the minus lambda, which is 1 over 125, times x, which is 10. So that's 1 minus e to the minus 1 over 125 across square root of a fraction times 10. And that gives me 0.0769 to 3 significant figures. Now another thing that you might have noticed is that this time we're talking about meters, we're not talking about time. Time is just a term that I've used, but if it says in a question, let's say for instance that the number of errors in a piece of fabric that's being created is 1 every 3 meters, okay, then we're not going to measure the distance between those Poisson events as actual time. We would measure it as the distance. We'd measure that as meters. So it's the time between the events, or it's the distance between the Poisson events. Whatever the Poisson events is in terms of, the exponential distribution is going to represent the time between those. So just be careful with that. So B, again, very similar to part C. So we're going to have the probability of x being less than 200 minus the probability of x being less than or equal to 100, because it doesn't say inclusively, but as I've said before, that won't make a difference. So that means that we'd have 1 minus e to the minus 1 over 125 times 200 minus 1 minus e to the minus 1 over 125 times 100. And like I said, this last set of brackets here is very important. You need to make sure you've definitely got those. So like I said, 1 minus e to the minus 1 over 125 times 200 minus 1 minus e to the minus 1 over 125 times 100. And that's given us 0.247 to 3 significant figures. So I'd like you to pause the video and give the Now You Try question to go. I just want to point out that this time it says that the parameter is 0.08 hours, not the mean. This is talking about the parameter. So straight away here, we have x squiggle exp 0.08. So it's different from what the example one was. So like I said, I'd now like you to pause the video and give the Now You Try questions a go. So hopefully you've paused the video and given the first Now You Try question a go. So here we have Olaf is employed by an engineering firm to watch a monitor and to give warning when the monitor signals that action is needed to adjust the production process. The interval between successive signals follows the exponential distribution with parameter of 0.08 hours. Find the probability that the interval between the next two signals is, so here we're using, like I said, x follows the exponential distribution with a parameter of 0.08. So A, less than 2 hours, so we're looking at probability of x being less than 2, which means that we have to do 1 minus e to the minus 0.08 times 2, which gave us 0.148 to 3 significant figures. For the second one, we're looking at longer than 50 hours. So remember that we're doing 1 minus the probability of it being less than or equal to 50 hours, which gives us 1 minus, in a bracket, again this bracket's very important, 1 minus e to the minus 0.08 times 50, which gave us 0.0183, which we can see there just at the top of my calculator still. Then for part C, between 10 and 20 hours, so again it doesn't say inclusively, but that wouldn't make a difference. So we've got the probability of x being less than 20 minus the probability of x being less than or equal to 10, which gives us 1 minus e to the minus 0.08 times 20 minus 1 minus e to the minus 0.08 times 10, which again you can still see in my calculator here, which gave me 0.247. Now for part D this time, it says if it has been 14 hours since the last signal. Now, like I said before, because the exponential distribution has no memory, that means that that bit there we can just ignore. Okay, that doesn't make a difference to what we're going to be calculating next. What is the probability that the next one will not occur for at least another 14 hours? So then we're looking at the probability that x is more than 14, which is the same as 1 minus the probability of x being less than or equal to 14, which again gives us 1 minus, in a bracket, 1 minus e to the minus 0.08 times 14, which gave us 0.326, okay? So this bit of information here didn't make a difference to what we ended up doing here because the exponential distribution has no memory. Moving on to the second Now You Try. Again, if you haven't done this yet, pause the video and give it a go. So hopefully you paused the video and you gave the Now You Try a go. So here we have a random variable x has a probability density function, and it's written out there, which means that we're using x squiggle exp 3.2 because that's our lambda, our parameter. Then we're trying to find the probability of x being less than 2.5, which means that we're doing 1 minus e to the minus 3.2 times 2.5, which gives us 0.999664537. And again, you can see there that I haven't rounded that to 3 significant figures, because if I was to round it to 3 significant figures, I'd get 1.00, which wouldn't tell me anything. So I've just wrote out the whole number. B, greater than 4.1, which means we do 1 minus the probability of x being less than or equal to 4.1, which would give us 1 minus, in a bracket, very important, 1 minus e to the minus 3.2 times 4.1, which gave us 0.0000200. And you can see that there still in my calculator. Part C, between 2.4 and 4.2. That means that we're doing the probability of x being less than 4.2 minus the probability of x being less than or equal to 2.4. Again, that less than or equal to doesn't change how we are going to be doing our working. So then we've got 1 minus e to the minus 3.2 times 4.2 minus, in a bracket, 1 minus e to the minus 3.2 times 2.4, which ends up giving us 0.0000461. And again, you can still see that in my calculator there. I've just rounded it to 3 significant figures. For the last one, for D, we end up with 0. If you want to think about why this happens, then if you think that we can only work in terms of less than or equal to's, then what I'd actually be doing is I'd be doing 1 minus e to the minus 3.2 in this case times 2.3. So that would be my less than or equal to 2.3 minus, and then I'd take away the probability that we had strictly less than 2.3, which remember would end up being the exact same calculation. And you can see there that it gives us 0. So what I was putting in my calculator then, just to re-emphasise that, is I did the probability of x being less than or equal to 2.3 minus the probability that x was less than 2.3. So that all that would be left was the exact probability of getting 2.3. And as you can see, because we don't change our calculation at all, it ends up giving us 0. So this is the same as in the rectangular distribution, in the normal distribution. It's very important that you remember that. So next time we're going to have a look in a bit more detail about switching between the Poisson and the exponential distribution, and a little bit more about what the mean of the exponential distribution is telling us. Thank you very much for listening.